Have you ever wondered how an AI in a video game knows exactly when to attack or when to hang back? Or how a robot can learn to pick up an object it's never seen before? It all boils down to one fundamental question. How does a machine learn to make the absolute best decision to get what it wants? Well, in this explainer, we're going to pull back the curtain and see exactly how that works. Let's dive in.
All right, here's our game plan. We're going to build a learning machine right from scratch. First, we'll figure out how to put a score on different choices. Then, we'll hit that classic problem. Do you stick with what you know or try something new? From there, we'll look at a really slick solution, figure out how to make it run faster, and finally, we'll teach it how to learn in a world that never stops changing.
Okay, first things first. If we want an agent to make good choices, it needs some way to measure how good each choice actually is, right? We literally need to put a number on our decisions.
And that number is what we call the action value. Think of it this way. Imagine you're the agent, and your action is choosing a restaurant for dinner. Every time you go, you get a certain amount of satisfaction or happiness. That's your reward. The action value of a restaurant isn't about that one time you went. No, it's the average reward you expect to get over the long haul based on all your past visits. It's your gut feeling, but quantified.
So how do we actually calculate this thing? Well, the simplest way is called the sample average method. Now, don't let the formula on the slide intimidate you. It's way simpler than it looks. On the left, that Q of T of A, just think of that as our best guess for the value of a certain action A. The Q is just what we use in this field. So how do we get it? Look at the right side. On top, you're just adding up all the rewards you've ever gotten for taking that action. On the bottom, you're just dividing by the number of times you've taken it. It's just a simple average. So if you went to a restaurant 3 times and your happiness scores were 7, 8, and 9, your Q value would be 7 plus 8 plus 9, which is 24, divided by 3. So 8. That's it. It's just a running average.
Okay, so now our agent has these estimates, these little scores for how good each action is. The next, and maybe the most important question is, how does it actually use those scores to pick what to do next? And this brings us to one of the biggest challenges in all of reinforcement learning. I mean, the obvious thing to do would be to just look at our list of scores and always pick the action with the highest number, right? We call this a greedy strategy. But is being greedy really the best way to go in the long run?
This whole question pits two big ideas against each other. On one hand, you have exploitation. That's using what you already know to get the biggest immediate payoff. It's going to your favorite restaurant because you know it's good. On the other hand, you have exploration. That's trying something totally different, like that new place down the street, just to see if it might be even better. Here's the catch. You can't do both at the same time. You have to choose.
In this example right here shows exactly why only exploiting is a massive trap. So imagine restaurant 1 is secretly the best restaurant in town, a true 10 out of 10. But on your very first visit, you just have a bit of bad luck. The service is slow, whatever, and you rate it a 5. Then you try restaurant 2, and it's pretty good, an 8. A purely greedy agent, one that only exploits, would look at those two scores and decide, well, 8 is better than 5, so I'm going to restaurant 2 from now on. And it would go there forever. It would never go back to restaurant 1 to get more data and find out that its first low score was just a fluke. The agent gets stuck thinking it found the best, when the actual best option is right there, totally ignored.
So, if being a greedy agent is a trap, how do we get out of it? We need a smarter strategy. Something that lets us exploit our knowledge most of the time, but also explore a little, just in case we're wrong.
And the solution is actually beautiful in its simplicity. It's called epsilon greedy. Here's how it works. We just pick a really small number. We call it epsilon. Most of the time, with a probability of 1 minus epsilon, we just act greedy. We exploit. We pick the best option we know of. But every once in a while, with that small epsilon probability, we do something crazy. We completely ignore our scores and just pick an action totally at random. That's our exploration. To make that real, a super common value for epsilon is 0.1. What does that mean? It means our agent will be greedy and exploit its best known option 90% of the time. But for that other 10% of the time, it just throws caution to the wind and explores a random choice. That tiny bit of randomness is the secret sauce that keeps it from getting stuck.
And you don't have to take my word for it. The proof is right here in these graphs. Let's look at the one on the left, average reward. See that green line flatlining at the bottom? That's the purely greedy agent, the one with epsilon of 0. It learns a little bit and then just gets stuck. Now look at the blue line. That's our agent exploring just 10% of the time. It just keeps getting better and better, achieving a way higher average reward. The graph on the right tells the same story. The greedy agent gets stuck picking the best action maybe 40% of the time, while our exploring agent gets better and better until it's picking the optimal action almost every single time. It's just undeniable proof. A little bit of exploration goes a long, long way.
Let's really solidify this by walking through the table. At time 0, we know nothing. All our Q values are 0. At time step 1, we try action 1, get a reward of -1, so Q1 is now -1. Simple. Time 2, we try action 2, get a reward of 1. So now Q2 is 1. Now, pay attention to step 3. At this moment, our best guess for the best action is A2, because its value is 1. But look, the agent chose A3 instead. Why would it do that? That's our epsilon kicking in. That's an exploration step. It ignored what it knew and tried something random. It got a reward of -2, so now Q3 is -2. Okay, time 4. The greedy choice is still A2. This time the agent exploits, chooses A2, and gets a big reward of 2. So how do we update Q2? Well, we average all the rewards for A2. We had a 1 before, now we have a 2. So 1 plus 2 is 3. Divided by the 2 times we've tried it, our new Q2 is 1.5. See how that works? It's this dance between exploring and exploiting that helps it learn. So, we have a learning agent that works, but you might have spotted a little issue in that last example. To update our score, we had to remember every single reward from the past. What if we've tried an action 1,000,000 times? That's a lot of data to store and add up every time. There has to be a better way. And that brings us to our next section, finding a more efficient way to do this.
Right, so let's look at our original formula again. The problem is hiding in plain sight. It's that big summation symbol on top. It means that to get our new average, Qn, we have to go back and add up all n minus 1 of the previous rewards, every single time. If n is 1,000,000, that's 1,000,000 numbers to store and 1,000,000 additions to do. That's just not going to work for big problems. It's slow and it's a memory hog. We need something smarter. And of course, there is a better way. It's this incremental update rule, and it's honestly a beautiful piece of math. The goal is to get our new average using only the old average and the brand new reward we just got. After a little bit of algebraic magic, which you can see on the slide, we end up with this fantastic formula at the bottom. And this is what it says in plain English. Our new estimate is equal to our old estimate plus a little step in the direction of our new information. That Rn minus Qn part is basically the error or surprise. How different was the new reward from what we expected? And the 1 over n part is our step size. We're just nudging our old estimate a little bit towards the new reality. And the best part? We don't need to remember the history of rewards anymore. All we need is the last Q value and the count n. It's incredibly efficient.
And here it is, the whole shebang. This is the complete recipe for our simple learning agent. You start by setting all your Q values to 0, then you just loop forever. Inside the loop, you use our epsilon greedy rule to pick an action, either the best one or a random one. You take the action, get a reward, and then use that super efficient incremental formula to update your Q value. That's it. It's a complete, simple, and surprisingly powerful learning algorithm.
So we've built a really effective agent that can learn the best action in a world that's static, or what we call stationary. But let's be real, the actual world is almost never static. So what happens when the best thing to do today isn't the best thing to do tomorrow? Think about our restaurant example. Your favorite place might hire a terrible new chef, and suddenly the food is awful. Or a brand new, amazing restaurant could open up across the street. This is what we call a non-stationary problem. The rewards aren't fixed, they're changing over time. And our current agent, it's not built to handle that very well.
So why does our agent fail here? Well, the problem is that step size parameter, the 1 over n. As n gets bigger and bigger, 1 over n gets smaller and smaller. After 1,000,000 tries, the step size is practically 0. This means new rewards have almost no impact on its estimate. The agent basically gets old and stubborn and stops learning. The fix is brilliantly simple. We just replace that shrinking 1 over n with a constant value, which we call alpha. By keeping the step size constant, we're telling the agent to never stop learning and to always pay attention to recent experiences.
What this constant step size really does is it turns our simple average into a weighted average. Instead of every past experience having the exact same importance, this method gives more weight, more influence to the things that just happened. Old, outdated information from a long time ago matters a lot less, and that's exactly what you want when the world itself is changing. Now, this technique has a bit of a fancy name. It's called an exponential recency-weighted average. That sounds complicated, but it just means that the influence of old rewards fades away over time, and it fades away exponentially fast. The most recent reward gets the biggest say, the one before it a little less, and rewards from way back in the past have almost no influence at all.
So what we've really seen today is that building a learning agent is all about balancing these fundamental trade-offs, exploring versus exploiting, remembering the past versus adapting to the future. And this isn't just a problem for machines. It's a deeply human question, isn't it? When you face a new challenge in your own life, how do you decide when to trust what you've learned from past experiences and when it's time to throw that out and try a completely new approach for a world that has changed?